Now, when this diode is used in practical circuits, we will have to replace this diode with its equivalent circuit. So now we will draw equivalent circuits of diode. Equivalent circuits will be based on the biasing of diode. If diode is forward biased, if it will be replaced by different components in the circuit. If diode is forward biased, that is its anode terminal is biased at higher potential with respect to cathode terminal, as according to definition a diode conducts only in forward bias case. So seeing this diode as ideal, I will expect an operation that it should operate like a short circuit. So in a forward biased PN junction, it is replaced in the circuit with a short circuit when it is forward biased. And when in the question material of the diode is given, or I will say if the diode is practical, if the diode is practical, practical is identified with uh, either material is given or forward drop is given. If any of the quantity is given, any of the thing is given in the problem out of these two, the diode will be considered as practical diode. And for the practical diode, it cannot conduct until the applied electric field overcome the induced electric field across the junction. So in other words, I can say that diode cannot conduct until the applied forward voltage overcome the cutting voltage of diode. So uh, in this case, the diode will be replaced with a battery which is opposing to the supply voltage, and this battery has potential equal to V gamma. This is anode terminal, this is cathode terminal, and this V gamma equal to 0.2 volt for germanium and will be equal to 0.7 volt for silicon. This will be for germanium and zero point 0.7 volt for silicon. Last case, in some cases, forward resistance of diode is also given. Means a diode is operating in forward bias and offering some resistance. Obviously, it will be very small, but if it is given in the problem, it should be considered in the equivalent circuit of diode, and diode will be replaced with this forward resistance RF and cutting voltage V gamma. These are the equivalent circuits of a diode when it is biased in forward direction. If diode is ideal, it will be replaced with a short circuit, and if it is a practical diode, it will be replaced a cutting voltage, a battery with cutting voltage, and if forward resistance is given, it will be replaced with series combination of forward resistance RF and cutting voltage V gamma. The value of this resistance will be low. Second case, if a diode is reverse biased, we will have to replace it with its equivalent circuit. I will replace, I will interchange the terminals of diode. This is cathode terminal and this is anode terminal. For suppose this diode is reverse biased, and in the problem it is given that it is ideal diode, or even it is practical diode. In both the cases, when it is reverse biased, it will be replaced with a open circuit. This is cathode terminal and this is anode terminal. This means that a diode which is reverse biased does not conduct. It will be replaced with an open circuit. And next case is if diode is little bit conducting, means it is offering a very high impedance. In case of open circuit, impedance is infinite, but if it offering if it is offering a finite resistance which is given in the problem, that is reverse resistance RR, which will be very high, is given in the problem, then we will have to replace this diode with this resistance RR. Means diode is behaving like a very high resistance when it is operating in reverse bias, and ideally it is replaced with a open circuit, means it is not allowing to any current to flow through the diode. These are the equivalent circuits of the diode. When we will use this diode in practical circuits, it will be replaced with these equivalent circuits. We will see some examples. Calculate V and I. Calculate V0 and I. This is V0 and this is current I. Applied voltage is 30 volts. In this problem, uh, we are not given any specification about diode, and material is not mentioned, and no forward drop is mentioned. So we will consider the diode as ideal. Considering the diode as ideal, if it is ideal diode, it will be replaced with a short circuit when it is operating in forward bias. In the circuit, it is clearly seen that this diode is forward biased, so it will be replaced with a short circuit, and this resistance is 1 kilo ohm. So I can calculate the current through the diode I by applying the KVL. Minus 30 plus this current will flow through this diode, and a voltage drop will be there, I into 1 kilo ohm equal to 0. So I will be equal to 30 upon 1 kilo ohm will be equal to 30 milliamperes. And we can see that across these two terminals plus 30 volt is applied, and the whole plus 30 volt is going across the output terminals. So the output voltage V0 will be equal to 30 volts. Next question. Calculate I and V0. In this problem, in this problem, with the diode, its material is mentioned. As material is silicon, its cutting voltage V gamma will be equal to 0.7 volt. So in the circuit diode, first we will check that it is forward biased or reverse biased. According to the polarity of the battery, it is clear that this diode is forward biased, and we can replace this forward biased P injection with its cutting voltage, which is equal to 0.7 volt. Now it is clearly seen that across these two terminals we are calculating the output voltage, and across these two terminals a battery is connected between them, zero point 0.7 volt. So it is clearly seen that V0 equal to 0.7 volt. Also current I can be calculated as minus 30 plus I into 1 kilo ohm. This will be current I through this resistance, and this will be voltage drop across this. Minus 30 plus I into 1 kilo ohm plus 0.7 volt equal to 0. From this KVL equation, I will calculate 30 minus 0.7 divided by 1 kilo ohm equal to 29.3 milliamperes. This will be the current through diode, and this is the voltage across the diode. Next, In this question, we are asked to calculate a V0 voltage, and the parallel combination of two germanium diodes is used. From the supply voltage, it is clearly seen that both the germanium diodes will be forward biased, and we can replace both the diodes with their equivalent circuits. As material is mentioned, with these two diodes will be replaced with their equivalent circuits, that is 0.2 volts. And now the voltage V0 can be calculated. V0 can be calculated. First we will have to calculate the current, or another technique is there to calculate V0. We will replace this V0 with a battery for some time to calculate V0. I will replace this 10 volt with a battery, and other end will be grounded. This is 10 volt battery, and I will apply a KVL in this loop and can calculate V0. With the KVL equation in this loop, minus 10 volt plus 0.2 volt plus V0 equal to 0. Therefore, V0 will be equal to 10 minus 0.2 equal to 9.8 volts. V0 will be equal to 9.8 volts. Next question. Now, calculate V0 in this circuit. There is a parallel combination of a germanium diode and silicon diode. When two diodes are connected in parallel, one is germanium diode and other is silicon diode. If we will replace both the diodes with their equivalent circuits, as it is clearly seen that both the diodes are forward biased, if we replace both the diodes with their equivalent circuit, one will be replaced with the 0.2 volt germanium diode and other will be replaced with 0.7 volt. In this particular part of the circuit, there are two parallel branches, one is this and one is this. In these two parallel branches there are different voltages, but according to KVL Kirchhoff's voltage law, in parallel branches there cannot be two different voltages. So either this diode will be off, either or this diode will be off. So both the diodes connected in parallel cannot conduct at a time. Uh, you can remember for this concept for solving any other problem, that if two diodes are connected in parallel, then only the diode with lower cut-in voltage will conduct. If the diode with lower cut-in voltage will conduct, then we will draw the circuit as germanium diode has lower cut-in voltage 0.2 volt, while silicon diode has higher cut-in voltage, so it will not conduct, and if diode is not conducting, it will be replaced with an open circuit. It will be replaced with an open circuit. Now I can replace this 10 volt with a battery, and I can replace this V0 with a battery. Now I can calculate this voltage V0 by applying loop KVL in this loop. Minus 10 volt plus 0.2 volt plus V0 equal to 0. Therefore, V0 will be equal to 10 minus 0.2 volt equal to 9.8 volts. 9.8 volts. Now, next problem. For a PN junction, PN junction. Na equal to Nd equal to 5 into 10 raised to power 15 per centimeter cube, and Ni equal to 1.5 into 10 raised to power 10 per centimeter cube. Calculate V naught at T equal to 300 degrees. Calculate. Assume Vt equal to 25 millivolt. We have to calculate contact potential V naught. We know that contact potential V naught equal to Vt log to the base e and A into Nd upon Ni square. Now substituting all the values, Vt equal to 25 into 10 raised to power minus 3 log to the base e 5 into 10 raised to power 15 into 5 into 10 raised to power 15 divided by 1.5 into 10 raised to power 10 whole square. The contact potential comes out to be 0.636 volts. Next problem. For a PN junction, V naught equal to 0.7 volt, epsilon R equal to 12, epsilon naught equal to 8.85 into 10 raised to power minus 14 farad per centimeter, Na equal to Nd equal to 5 into 10 raised to power 15. Calculate depletion layer width, depletion layer width. We know that depletion layer width W equal to under root of y epsilon upon q into 1 upon Na plus 1 upon Nd into V naught. Substituting all the values, W equal to under root of 2 into 12 into 8.85 into 10 raised to power minus 14 divided by 1.6 into 10 raised to power minus 19 coulomb into 1 upon 5 into 10 raised to power 15 plus 1 upon 5 into 10 raised to power 15 into contact potential V naught, that is equal to 0.7 volt. Solving for this, we get W equal to 6.096 into 10 raised to power minus 5, which is equal to around 60.96 micrometers. This is in centimeters. Sorry, this is in centimeters. So this will be 6.096 into 10 raised to power minus 7 meters, and it will be 0.61 micrometers. This is the depletion layer width in PN junction. Next question. For a PN junction, V naught plus VRB, yep, V naught plus VR equal to 2 volt and W equal to 1 micrometers. If V naught plus VR equal to 8 volts W will be equal to what? A similar question once was asked in GATE examination. Uh, we know that depletion layer width W equal to under root of twice epsilon upon Q into 1 upon Na plus 1 upon Nd into V naught plus Vr. Now from this we can write W is directly proportional to root of V naught plus Vr. If depletion layer width is W1, then voltage will be V naught plus Vr1. If depletion layer width is W2, then voltage will be V naught plus Vr2. Dividing both the equations, W1 upon W2 is inversely directly proportional to V naught plus Vr1 divided by V naught plus Vr2. This gives W1, which is 1 micrometers, 1 micrometers upon W2, which is to be calculated equal to in the root of 2 upon 8. So solving this equation, we get W2 equal to 1 micrometers into root 4 equal to 2 micrometers. Capacitances in diode. Consider a parallel plate capacitor. Now we know that this is a capacitor, but if we want to check that really if it is a capacitance, then it should behave in this manner, that if we change this voltage V applied across this capacitor, then the charge deposited on the plates of capacitor should also change. So if we experience change in charge with change in voltage, means change in charge dq across the plates with the change in voltage, if there is change in charge deposited on the plates with change in voltage, then we can say that this is a capacitor. Same concept will be applied in PN junction diodes also. There are two type of capacitances in PN junction diode. One is transition capacitance and another is diffusion capacitance. Both the capacitances remain there always simultaneously in a diode, but depending on the biasing, uh, one of the diodes dominates from, depending on the biasing of diode, one of the capacitance dominates. First we will study about transition capacitance. Consider a PN junction. It is connected across a battery with this polarity. For this PN junction, this is N layer and this is P layer, and at the junction this is depletion layer. On the N side there is positive ion and on the P side there is negative ions in depletion layer. Remember that there are no free charge carriers in depletion layer because all the charge carriers are removed from the depletion layer, hence it is called depletion layer. In p-type semiconductor, majority charge carriers are holes, and in n-type semiconductor, majority charge carriers are electrons. There are few holes in n-type and there are few electrons on p side. Now if this diode is reverse biased, then as we already studied that when a p-n junction is reverse biased, the depletion layer width of a p-n junction diode widens. Means depletion layer width W increases with increase in voltage, reverse voltage across the diode. If we increase this reverse voltage, depletion layer width will increase. So if we increase this reverse bias voltage, the depletion layer width of diode will also increase, and it will look somewhat like this. Earlier the depletion layer width from year to year, but now the depletion layer is increased with increase in reverse bias voltage. In this depletion layer, we are seeing that this charge, positive and negative charge in the depletion layer, I can call it positive and negative ions. Both are charges. I can call them uncovered charge. Remember, positive ions are also there in this region, but this positive ions are covered by electrons in this region, and also negative ions are there in p side. These negative ions are covered by holes in p side, while the charges, the ions in depletion layer are uncovered charge. So with change in reverse voltage, with increase in reverse voltage, we are observing that the depletion layer width is increasing, and if depletion layer width is increasing, the uncovered charge in the depletion layer also increasing. So we can say that there is change in uncovered charge with respect to change in voltage, and this is a capacitive effect. This capacitance is called transition capacitance CT. So I can define now transition capacitance CT as CT is due to the change in uncovered charge in the depletion layer with with change in voltage. And remember, this capacitance dominates over diffusion capacitance in reverse bias diode. So transition capacitance is also called as depletion capacitance or space charge capacitance. Space charge capacitance, and mathematically it is given by CT equal to epsilon W by CT equal to epsilon into A by W, where epsilon equal to epsilon naught into epsilon r. Epsilon naught is permittivity of free space, and epsilon r is relative permittivity of semiconductor, whichever is used. It may be germanium or it may be silicon. If it is germanium, then epsilon r equal to 16, and if it is silicon, epsilon r equal to 12. where A is cross-sectional area of diode, cross-sectional area of diode, and W is width of depletion layer. W is width of depletion layer. Now, transition capacitance CT equal to epsilon A by W, and we know that depletion layer width W is under root twice epsilon upon Q into 1 upon Na plus 1 upon Nd into V naught plus VR, reverse bias voltage. In this equation, we can easily see that W is directly proportional to V naught plus VR, and yesterday we saw that this voltage is very much greater than this voltage, so I can say W is directly proportional to root of reverse bias voltage. If W is directly proportional to root of reverse bias voltage, CT is inversely proportional to V naught plus VR, and CT is inversely proportional to root of reverse bias voltage. Now, I will discuss some things about fabrication of diodes, but there are three types of PN junction diode. There are three procedures of fabricating diode. One is step graded. For this step graded junction, we are studying all this theory, and one is linearly graded, and one is diffused junction. In step graded PN junction, a single piece material, either P type or N type material is taken, P type material, and half of that diode is doped with donor type impurity, so it becomes N type region. In linearly graded diode, an N type material is taken and other material is grown over this N type material, and this becomes a PN junction. In diffused junction, it is formed in the form of IC. It is fabricated in the form of IC. This is N-type region, and this particular region will be doped with P-type impurity. This is diffused PN junction. I am discussing all these things because in the examination it is asked that how CT varies with reverse bias voltage for these PN junctions. From this equation, I can write that CT is inversely proportional to reverse bias voltage raised to power m. If m equal to 1 by 2, if m equal to 1 by 2, then it will be under root m. So if the diode is step graded, the value of m will be equal to 1 by 2. Means CT will be inversely proportional to root of reverse bias voltage. If diode is linearly graded, then M is equal to 1 by 3 and CT is inversely proportional to cube root of reverse bias voltage. And if diode is diffused junction, then M equal to 1 upon 2.5 and CT is inversely proportional to reverse bias voltage raised to power 1 by 2.5. This will be the variation of capacitance. This was all about transition capacitance or space charge capacitance or depletion capacitance.